We are starting with alkynes, the fragmentation patterns of alkynes. They show intense molecular ion peaks, and in the case of terminal alkynes, strong M-1 peaks are obtained. The other prominent peaks are M-15. This is due to the elimination of a methyl radical, and M-29, M-28, etc. These three are the common peaks observed, and peak at M by Z is equal to 39 is obtained due to propargyl cation, due to the formation of propargyl cation. This is resonance stabilized. Okay, we can see the fragmentation patterns, all these things, by taking an example of 1-pentyne. 1-pentyne. One pentyne is CH triple bond C, CH2, CH2, CH3. The first peak obtained will be its molecular ion, that is at M by Z is equal to 68. That will be the molecular weight of 1-pentyne. First fragmentation, let's see. Number 1, by the elimination of methyl radical, CH3 dot is eliminated, and the remaining one you will get as a positive charge or carbocation. That will be CH triple bond C, CH2, CH2 plus, and the M by Z value of this peak is at 53. Okay, this is the M minus 15 peak. Okay, 68 minus 15 will give you 53. So this is the M minus 15 peak. And the second mode of fragmentation, in the second mode of fragmentation, ethyl radical is eliminated. C2H5 dot is eliminated. And the resultant one, it will be CH triple bond C, CH2 plus. Okay. And this is what referred to as the propargyl cation, which is resonance stabilized. I'll show you the resonance stabilization. It may come like this, and you will get CH double bond C double bond CH2. Okay. So this is the resonance stabilized propargyl cation, and this comes at M by Z is equal to 39, and this is the base peak. Okay, this is the base peak. And the third one is mode of fragmentation. I told you that in the case of terminal alkynes, M-1 peak is also prominent. So M-1 peak is obtained by the elimination of H dot, and the remaining one will be this one, C triple bond C, C3, H7, that is CH2, CH2, CH3. Okay, this is the molecular ion peak. This is at 68. So M-1 will be at 67. Okay, these are the prominent peaks obtained in the case of 1-pentyne. And if we draw the spectrum, it will be like relative abundance against M by Z value. And this is the molecular ion peak. In the case of alkynes, that is prominent molecular ion peak at 68, and M-1 peak is also very much visible. That will be just next to that one, 67. Okay, this is the M-1 peak, and you will get a peak at 53. That will be, intensity will be less. This is M-15 peak, and the base peak will be at 39. M by Z is equal to 39. This is the base peak. Okay, 39, at 39 you will get the base peak. At 67 there is a prominent peak, that is M-1 peak, and the molecular ion peak is at 68, and it is comparatively strong. Okay, with this alkynes, the discussion on alkynes is over. And next is aromatic hydrocarbons. Aromatic hydrocarbons. The most common and important aromatic hydrocarbon we know is benzene, that is C6H6. We know that it is very much stable and all. That's why its fragmentation is normally not done using our normal setup. Okay, so that means the fragmentation of benzene requires a great deal of energy, so it is not usually observed. Okay, and when it is attached with the side chain, it normally gives the corresponding characteristic mass spectrum. Okay, so when benzene ring contains a side chain, it is normally cleaved from the benzene ring to form a benzyl cation. And the benzyl cation, let me write, if it contains a side chain, benzyl cation is formed. Normally, benzyl cation is formed, and that rearranges to tropylium cation. Okay, this is the normal fragmentation pattern when it comes to the substituted benzenes. So let's check with ethyl benzene with the example of ethyl benzene. Okay, we are taking the example of ethyl benzene, and ethyl benzene is this one, CH2CH3 dot plus. The MBZ value is at 106. That is the molecular weight of this ethyl benzene. So the side chain is eliminated. The first one, methyl radical, first mode of fragmentation, that is methyl radical is lost, and the remaining part is a benzyl carbocation. You can see here. Okay, this is the benzyl cation. This is the benzyl cation, and this one rearranges to, this benzyl cation rearranges to tropylium cation. Okay, so the MBZ value of these two will be the same. That is MBZ is equal to 91. You will be wondering what might have happened here. Okay, I'll show you how did it happen. First, let us number these carbon atoms. Like I'm numbering it 1, 2, 3, 4, 5, 6, and 7. Okay, benzene ring and one CH2. There is a positive charge here. Okay, and now what happens is this carbon, this bond gets broken and this one gets attached to this first carbon. Upon the seventh carbon, second carbon attach. Now that attachment has changed to first carbon. As a result, what happens is that നോക്കാം, ഇതാണ് already ഉള്ള arrangement. You can write 2, 3, 4, 5, 6, and 7. Okay, so first carbon was outside, actually outside the benzene. Now it has come inside. അപ്പോൾ അത് ഇവിടെ കൊടുക്കുക. And here the double bonds are the same. ഇവിടെയാണ് double bonds ഉള്ളത്. And ഇവിടെ first carbon കൊടുക്കുന്നു, CH2 അല്ലേ, ഇവിടെ ഇങ്ങനെ കൊടുക്കാം. അപ്പോൾ നോക്കണം, ഇവിടെ നിന്ന് ഇങ്ങോട്ട് വന്നപ്പോൾ സെക്കൻഡ് കാർബൺ എന്ത് കിട്ടി, പോസിറ്റീവ് ചാർജ് വന്നു അല്ലേ, എന്ന് വെച്ചാൽ സെക്കൻഡ് കാർബണിന്റെ ഒരു ബോണ്ട് എടുത്തിട്ടാണ് അങ്ങോട്ടേക്ക് പോയിട്ടുള്ളത്. അപ്പോൾ ദിസ് ഇസ് പോസിറ്റീവ്, സെക്കൻഡ് കാർബണിന് പോസിറ്റീവ് ചാർജ് കിട്ടി. ദിസ് ഇസ് ദ ഫസ്റ്റ് കാർബൺ. ഇനി എന്ത് ചെയ്യുന്നു എന്ന് വെച്ചാൽ ട്രിപ്പിലിൻ കാറ്റോൺ വി ആർ ഓൾമോസ്റ്റ് ദെയർ. ഇനി എന്ത് ചെയ്യുന്നു, ദിസ് ഹൈഡ്രജൻ ഇല്ലേ, ഈ ഹൈഡ്രജൻ കംപ്ലീറ്റ് ആയിട്ട് എന്ത് ചെയ്യുന്നു, ഈ സെക്കൻഡ് കാർബണിലോട്ട് ഷിഫ്റ്റ് ചെയ്യും. അപ്പോൾ ഇവിടെ ഫസ്റ്റ് കാർബണിൽ എന്ത് വരും, പോസിറ്റീവ് ചാർജ് വരും. അപ്പോൾ if you write like this, നമുക്ക് നോക്കാം, ഇത് 1, 2, 3, 4, 5, 6, and 7. അപ്പോൾ there is a double bond in between second and third carbon, that's okay. Double bond between fourth and fifth, that's okay. Between 6th and 7th, that's also okay. പിന്നെ എന്തായിരുന്നു, സെക്കൻഡിനായിരുന്നു പോസിറ്റീവ് ചാർജ്. നൗ ഇറ്റ് ഹാസ് കം ടു ഫസ്റ്റ് കാർബൺ, ബിക്കോസ് എന്തുകൊണ്ടാണ്, ഇവിടുത്തെ CH2 ഉണ്ടായിരുന്നു, വൺ ഹൈഡ്രജൻ ഹാസ് ഷിഫ്റ്റഡ് ഫ്രം ദിസ് കാർബൺ ടു the second carbon. Now tropylium cation is tropylium cation is formed. Okay, and now അറിയേണ്ട ഒരു കാര്യം എന്താന്ന് വെച്ചാൽ this doesn't stop here. Okay, M by Z is equal to 91, a prominent peak ആണ്, but the fragmentation doesn't stop there. It continues to expel another acetylene molecule. Okay, so how does it happen? This is the tropylium cation. Its M by Z value is at 91. We have seen that. Now from here an acetylene molecule is expelled. CH triple bond CH, a complete acetylene molecule is expelled, and the remaining one you can see here. I'll show you how it is expelled. See, from here an acetylene molecule gets eliminated, and the remaining ones acetylene, then this is 7 carbon system ആണ്, 2 carbon പോയി, ബാക്കി 5 carbon system ആയിരിക്കും. That is also, it will be like this. Okay, and the M by Z value of this species is 65. Okay, hope it is clear. And one more thing, there is a metastable peak. There is a metastable peak at M by Z is equal to 46.4. You might be remembering metastable peak M star. M star എങ്ങനെ കിട്ടിയത്? M2 square by M1 അല്ലേ? അപ്പോൾ ഇവിടുത്തെ M2 is 65. So this is obtained by എങ്ങനെ 65 in the square by 91. That will give you 46.4. Okay, there's a metastable peak at M by Z is equal to 46.4. Okay, now second mode of fragmentation in the case of the same ethyl benzene. We are discussing about ethyl benzene. We have discussed one mode of fragmentation. First, benzyl cation was formed, that is rearranged to tropylium cation, and this tropylium cation gets rearranged to another cyclopentadienyl cation by the expulsion of an acetylene molecule, and that simultaneously is the reason for the formation of this one metastable ion peak also, metastable peak also. And the second route is rather simple. In the second route, instead of methyl radical, ethyl radical gets eliminated, that is minus C2H5 dot. If that is eliminated, you are left with this one, benzene ring with a positive charge, and from here, like as I have explained here, an acetylene molecule C2H2. C2H2 can be eliminated like this, and you will get a cyclobutadienyl cation. Okay. For the sake of understanding, to make it more clear, we can depict this bond as these two dots, radicals, and this is, suppose this is also cleaved like this, and then these two radicals combine to form another bond, that is CH triple bond CH, and these two dots get combined, and that will result in this species. Okay, formation of this species. And this is M by Z value is 106, and the M by Z of this one is 77, and the M by Z of the final species is at 51. In the case of ethyl, the discussion regarding ethyl benzene is over. Now another one, and I'll be discussing only the prominent peak, that is isopropyl benzene. Its name is more familiar, not as isopropyl benzene. It has a short name or nickname called cumi. Okay, that you have seen in the case of the preparation of phenols. That phenol is normally prepared from, the starting material is cumi, right? So the normal way, that is methyl radical is eliminated, CH3 dot is eliminated, the remaining species is CH plus CH3, and this can rearrange. This can rearrange like this to form a tropylium cation derivative. Okay, please work it out for your own. Okay, you will get neatly as I have explained in the case of tropylium cation. You can get the species for sure, and the MBZ value will be at 105. Okay, and this is the normal fragmentation methods in the case of aromatic hydrocarbons. There is a possibility of another one, that is the McLafferty peak. Okay, you might be familiar with the conditions of the requirements of McLafferty peaks by now. That is, there should be a gamma hydrogen. Okay, gamma hydrogen abstraction followed by alpha beta cleavage. This is the requirement, or this is what happens in the case of McLafferty rearrangement. Okay, so all hydrocarbons, if the benzene ring contains 3 or more carbon atoms, okay, when the side chain connected to benzene ring contains 3 or more carbon atoms, McLafferty rearrangement definitely takes place to give a peak at M by Z is equal to 92. Okay, 1, 2, 3, and 4. This is the normal butyl ring, normal butyl chain attached to benzene ring, and we need only gamma hydrogen. Here available alpha, beta, gamma, and delta carbons are there. Okay, but what we want is this gamma hydrogen. Okay, now gamma hydrogen abstraction followed by alpha beta cleavage. So this double bond abstracts this gamma hydrogen. Here a bond is formed like this, and here this alpha beta bond is cleaved like this, and the resultant species obtained is here. There was one hydrogen initially and one more hydrogen got attached. So here you can show like this, and alpha beta, this bond with alpha has become a double bond. Okay, and this is the species which has M by Z is equal to 92. Okay, this species is responsible for the McLafferty peak. And don't forget the remaining one, that's the remaining chunk piece, is CH2 double bond CH, CH3, propene in the case of this compound. Okay, the starting material we have taken. So this is all about aromatic hydrocarbons. In the case of examination point of view also, this is important. Okay, because you could witness changes in the pattern. Okay, in the case of alkenes and alkynes, we have seen somewhat similar pattern, but in the case of aromatic hydrocarbons, it changes. Okay, we have discussed ethyl benzene, cumene, and this McLafferty peak. Okay, hope it is clear for you people, and this is the end of today's session. Thank you.